Right. First thing first, in radioactivity, right? Before we take a look at before we take a look at types of particles, we need to remember the Geiger-Marsden experiment, right? Somebody has to go over that yesterday, right? Right. So we should remember that in the Geiger-Marsden experiment, they took cold foil and they took an alpha source and they shot alpha particles at the cold foil. And you would have recognized that most of them went straight through, right? A small amount was deflected and an even smaller amount was reflected, okay? Right? And the conclusions were, number one, the atom mainly had what? Empty space, right? The second conclusion is that the atom had a small positive core. Atom has a small positive core. And the third thing is that the core, because it hit it and went right back, it meant that the core was small and dense, right? And from that, they came up with the model of the atom. We know it has a nucleus in the middle, and that nucleus has protons and neutrons. And around it have your electrons, right? So they came up with those small things, right? So if they actually explain Geiger-Marsden, it's the same thing from form 5. Right? After that, we should have a little idea about a few particles. Alpha particle, the beta particle, and the gamma particle. How is radiation produced? That is when excited particles lose energy. And these excited particles, when they lose energy, right, the energy that is given off is in the form of these types of radiation, alpha, beta, and gamma. So we need to remember about these things, right? Alpha, beta, and gamma. Alpha is a helium atom, 4,2 helium atom with a charge of +2. Beta is an electron, right? Charge -1, of course. And gamma is just pure energy. Right? Can we open the door? No. Look, somebody money on Instagram. Just pick it up, put it on my table. I don't want them to fall short. All right. Nice. Right. So you have alpha, beta, and gamma particles, right? So we have to remember what was top of alpha particle. Anybody remember? Paper. Right? A sheet of paper. What was top of beta particle? Anybody making payments today? No. All right. Millimeters of aluminum and gamma, just a few centimeters of lead. Right? So we remember those little things about it, right? We have to also remember if a particle loses a helium atom, what does happen to it? It loses a mass number of 4 and an atomic number of 2. If a particle loses a beta, the mass number stays the same and the atomic number increases by 1. If it loses a gamma, just energy it will lose, right? That's okay. And then you can balance the equations. Right? Next thing that we need to remember about radiation, we need to remember if I have an electric field, how the beta does behave. Right? Where would the alpha go? The alpha will go towards the negative. The beta will go towards the and the gamma will go straight through. Right? You also now have to be able to use Fleming's right-hand, left-hand rule to determine what will happen if they pass through a magnetic field. Right? If you use Fleming's left-hand rule, X means what? In or out? In. So the magnetic field going in, there's a positive particle, so the positive particle going towards me. So therefore the force exerted here is upwards. So the force exerted here will be upwards. You can do the same thing, but you know what happens to gamma, right? Gamma going straight through. Beta is what? Right? Magnetic field going in. If a negative charge going towards me, then the positive charge going away. So this finger is away. Right? So therefore, the force is down. And the path is shorter. Why again? Why is the path shorter? Because the beta is smaller and lighter. Okay? So that's your electric fields, right? So that's the Form 5 stuff. The next thing that we need to remember on the Form 5 stuff, well, we'll do a formula for half-life, but we need to remember about Einstein's energy mass relationship. So during a reaction, the reactants are converted into products. The reactants are converted into products. So if you find the mass of the reactants and the mass of the products, there's a change in mass. Right? There's a change in mass. So if you find that mass, you'll get that value. Most of the time, you'll get it in U. So you can take the change in mass and multiply it by 1.67 or 1.66 by 10 to the minus 27. That will take your mass and convert your mass to kilograms. That's okay? And then if you have your mass in kilograms, we could find the energy by taking the change in mass and multiplying it by the speed of light squared. Right? You should know what C is, right? So all these are little Form 5 things that you should know. In Form 6 now, Unit 2, they expect you to know that if I have activity or N naught, it don't matter. They expect you to know that this function for activity will look like this: A naught e to the minus lambda t, or N is equal to N naught e to the minus lambda t. And you should know that A is equal to lambda N, A naught is equal to lambda A naught, N naught. What's lambda again? Right? That is your decay constant. Somebody say wavelength. A is your activity in Becquerel. Right? And well, these are your original values, right? These are your original values. That's okay? So this function here for this graph is exponential. That's okay? And then if we do the little proof, which I'll show you one time because it's real easy. If N is equal to N naught on 2, then T is called your what? T is called your half-life. Right? T is called your half-life. So if I substitute that in here, I'll get N naught on 2 is equal to N naught e to the minus lambda half-life. I think I showed you this yesterday, but if this will cancel, right? And you find ln on both sides, you will get ln half is equal to minus lambda half-life. If you rearrange and you solve for half-life will be equal to ln 2 over lambda. Sorry? Yeah, everything here in the notes except for that first one. Yeah, the minus, no, ln half and minus. Okay, so these are the things that you need to remember about radioactivity. All right, so let's try a few in these now. Oh, one thing I forgot to mention. Right, you remember binding energy per nucleon, right? So if you have binding energy per nucleon, right, by the nucleon, you'll get an idea of the stability of objects, right? And there's a little graph that you have to learn, right? Something like that, right? And the iron is the highest, and all these here are your transition metals, right? Some of the more stable atoms are the transition metal. Okay, so you find binding energy per nucleon. What is that? Right, but how you find binding energy? This here is the energy required to break up the atom. So if you work out this and divide it by the number of nuclei, you'll end up with the binding energy per nucleon. Right? So those things that we need to remember, right? Twenty 24 had a piece of radioactivity in it, huh? A piece of radioactivity at the end. 2019, 21, 22, 22. Oh, no, I was wrong there. All right, 2022, right? 2022, number 3. All right, let's start here one time. 2022 number 3. Two number 3, yeah. Ready? Right? What's your activity? The rate at which a radioactive substance decays, right? And the SI unit is Becquerels, nice. The rate at which a radioactive substance decays, right? SI unit Becquerels. What is decay constant? Probability per unit what? Per unit time, right? The probability per unit time that a nuclei will decay. Probability per unit time that a nuclei will decay. That's why decay constant has half-life in it. That's why it's used to calculate the probability. SI units, which is technically Hertz, right? But it's not Hertz. S to the minus 1. Next one, half-life. Time taken for probability per unit time Nikolai, you know, I can come was decay constant. Probability per unit time that a nucleus will decay. Half-life is time taken for half of a present element to decay. SI unit will time, right? Second. Right, all of them simple, like just pay attention to the K constant, right? We tend to forget that. Let's move on one time, find the half-life here. Take your time, right? To get half-life, you need to get the K constant. Write down the info to give you and see whether you can how you can work it out. Well, just know that it will be in minutes. And then, but they want half like an hour. That's the book. Alright, ready? Y'all done? Lily, I can't money boy move it out. Lily, I have to hold hand. Right, just checking to see what you have, right? The initial activity. The initial activity is 2000, so that's A naught. After 4 hours and 20 minutes, so that's time, right? That's what, 260 minutes. The activity decreased to this value here, right? So that's a new activity. So you need to find lambda. So there are two ways you can do it. Well, what is it? One main way you can do it, right? Because we don't know lambda. We're going to use A is equal to A naught E to the minus lambda T. Right? Remember, non-math people I gave you this, right? I told you that ln A over A naught is equal to minus lambda T. Right? I gave you that yesterday, right? So for those who are not doing math, you can learn that. So therefore, lambda is equal to ln A. A was 2400, A naught is 3000. And then divided by minus T, 206. So your answer will be in minutes, right? What I get for lambda there? Too much. How much you all got? In minutes, using this value here. 8.5 by 10 to 9. 8.5 by 2. What I got? 8.58. Right? Sorry, minutes. Minutes, right? And now you want to get half-life. right? Half-life will be ln 2 all over. Can we convert this value to, well, we can work it out in minutes and then convert it, right? So that'll be 8.58 by 10 to the minus 4. So that's ln 2 over what? Right? I got 807.9 minutes. Right? And then just divide that by 60, and you'll get 13.5 hours. Half-life is 13.5 hours. Pardon me? Somehow you did it. Minus? Yeah, if you want to use the long rules, yeah. Oh, your value is seconds? Yeah. Yeah, that should give you the same thing. You got the same answer in the end? Okay. All right, yeah. I have that too, but I just rounded off the piece of the figure. Let's go again. Any questions? Take another time. Wait till you're answer, right? Wait till you're answer, Ready? Next part. Oh, am I writing? Sorry. Am I writing? No? So that was 7 marks. Next part. Iodine 1, 2, 3 decays by iodine 1, 2, 3 decays by electron capture to beryllium 1, 2, 3 emitting gamma rays. Right? Emitting a gamma ray of that particular value, 159 K electron volt. Find the energy of this photon in joules. How are we doing that? How are we doing that? Anyway, how are we doing that? How are we doing that then? Convert to joules. What to do? Multiply by what? By charge by electron, right? The charge. Yeah, it will be positive. How much is that? 2.54 by 10 to the minus 14 or 15. 159, right? 14. 14. Yeah. And let's go again. Part C. Part C, I'm going to handle the N on N naught and ln, right? I'll just take from the table. Plot a graph of ln. So plot a graph of ln N on N naught versus T. And do a best fit. So that's best fit line you got, right? So the question I want to ask is, if you plot a graph of ln N over N naught versus T, and you got a best fit line. Let's say I give you a graph like that, right? What does the gradient represent? Non-matched equal linearize it fast now. Everybody, linearize it. What you end up with? How you do that? Come on, what you do now? Without looking at your book. Right? Carry across the end north and then find line on both sides. Right? And you have it there. Right? This is your y-axis. This is your y-axis. This is your x-axis. So your gradient is minus lambda. All right? Remember that, please. So the readings are no longer reliable when they fall between, or when we need the graph for that. Okay, I don't want to make sure you know what the gradient represents, right? Part 4, state two properties of a radioisotope which make it suitable for the use in nuclear medicine. Short half-life, and what else? All right. But what I'm looking for, besides short half-life, I'm looking for they have the ability to penetrate, so you can actually detect them, right? So they could penetrate the body, so you can detect them using some kind of device. So number one, they have short half-life and they are penetrable. All right, they have high penetrating power. Right, that was 2022. Let's check 2021. Oh, 1 second there. Part 2, yeah, 2021, you ask the question. Yeah, but look part now, huh? Yeah, part C. $10. 2021, part C. Oh, by the way, describe how carbon dating is used to find the age. What is do? Huh? Right. Huh? Right. So basically, if you have an object, let me see that object there. What you do is you take carbon out of it and see how much it has in grams. Right? And because carbon has a very very long half-life, then basically it is simple way to explain it, right? What they will do is they'll go to the carbon decay curve, right? Which will give you the mass versus the time. And they can take a look at the mass, right? Take a look at the mass value that they obtained, and then read off the time. And read off the time with it. A1, make it right? And check out the time it takes for it to reach a particular mass, right? So you're taking an object, taking the carbon out of it, and you're seeing what percentage of carbon it reached. Then you're going to the decay curve, and you're working out how old it is, right? That's one way. Or the next way is to use the formula, right? You can use the formula because it has a known half-life, right? It has a known half-life and a known decay constant, right? So if you know N naught, the original N naught is estimated, and you plug in your N value, and you know your lambda value, you can solve with T. All right? So there are different ways that they work it out, but that's one of the ways that they find the how old it is. Right, Shivish? Right, so the first step is to find the amount of carbon present in the sample. Right, and then using the decay curve, right, or the radioactive decay formula, and the known half-life, you can solve for the time or the age of the sample. All right, try part 2 and 3 now, please. Try part 2 and 3. Right, come on the board now, Timothy. Timothy, Vikash. Yes. You working it out? Oh yeah. You doing part 2 and 3. No book, eh? Take your time, write on what you have, see which formulas you could use. Right? These questions aren't difficult at all, right? We do one more and then we start electrostatics. All right, 31. Oh. That's explained to us already. Right, let's just check out your working on. right? So they gave you a sample, they gave you the atoms living in a wood, and they give you the decay constant. Find the half-life. How much years you all got? $5,724. Right? 5,723.8 years, right?
Oh, you get that.
Yeah.
After 24 years.
Yeah, round up, but always write the exact value. Always write before you round up, write that value, and then in the living wood in C part 2, 1 in 10, sorry, 1 in 10 to the power of 12 of the carbon atoms is C14. Calculate the rate of decay. So the accent for the activity, right, of carbon 14, right? Right, yeah, how we doing this? Huh? What we can do here? The rate of decay is activity. A is equal to 2 to the power n. I need to find number fraction of half-life, number of half-life. What we should do here earlier? So you want to get the rate of decay, so you want to get the activity. We can find it. Because they gave us the original number of atoms of wood. Yeah. So we can use A is equal to lambda n, yeah, that's good. Lambda is equal to give us there.
We have lambda already.
Right, so they gave you the original number. They gave you the original number of wood there. So all we have to do is find the original number of atoms there. So they said 1 in 10 to the 12 of carbon atoms is C14. So what to do? Right, no, how we getting at it? So you divide the 6.02 by 10 to the 23 by how much?
10 to the 12.
You divide that by 10 to the 12. So it means that your N value should be 6.02 by 10 to the 11. Yeah? 10 to the 11.
Which one are we using?
No, they gave us the original number of carbon atoms, right? 6 by 10 to the 23. So if we divide that by, question said 1 in every 10 to the 12 carbon atoms is C14. So we're taking the total and we're dividing by 10 to the 12 to find the number of C14, which is 6 by 10 to the 11. 6.02 by 10 to the 11. And then we multiply that by lambda. Sorry, you'll get by 10 to the minus 20. Huh? We do what? Yeah, we do one whole year now. Right, let's do a whole year an activity question.
So we get that straight. Yeah, but
Oh no, I don't know. I just listen to somebody. Sorry.
I think that.
How much you got? 2.31. Sorry. 2.31. That's it. 2 point.
Yeah.
If I don't see them.
Because yeah.
6.4. Yeah, 23 minus 2.
Like me this.
Wait.
One thing now, man.
What's that?
Make it more sense.
Take it back and see.
Yeah, but
All right, let's try one more now. One more before we change. Oh, sorry. May I try this? Yeah, sorry. No, you will tell me. I will tell you.
No, sir, I don't have a solution, sir. That's a mess. I wish this is a tree or something.
we didn't find out yeah.
All right, last one. We can ignore the A and B, right? Do this fast now. It's a multiple choice. Do this fast, and then I'll give you a whole year, right? Look out this fast. What? So the half life is 100 years, but it keep constant. Which one? Right, so it's just to divide ln 2 by that, right? All right, try this last one here. Ignore A and B, right? A and B is A and B in a difficult, right? B is unequal. Just try C now, please. Last one, right? Try C. Don't worry with the A, let's write it down.
And the result is what you got. 1.5 days.
Well, I get any of a book and a pen. Oh yeah, try part C and we done. Highest conjugate mass in number of atoms again. Highest conjugate mass in number of atoms.
You divide by C squared.
Chemistry people.
This stands up from the base.
I just convert mass to number of atoms. Mass no, yeah, it's something before that.
I just do IT.
What you have to do. So if you have 3.5 micrograms, how do you convert micrograms to the number of nuclei present?
Yeah, if you convert the micrograms to grams.
It multiply RMM or divide by RMM? So you divide by RMM and you multiply by Avogadro. Right? Oh yeah. Try this, please. Exclude Daria and Saraya. Do this one, please. Yeah, divide by RMM. The number. Yeah, divide by Hey, Nicholas Paul. Yeah.
Hey, what you I like this. I still have money in finance. Yeah. I see that. Yeah. What's small and what? So is that not well?
Yeah, right, so first part again, number of nuclei and note, right? So you're taking the mass by 10 to the minus 6, dividing it by the RMM, which is 11, and you're multiplying it by Avogadro's constant. Right, so I have 1.92 by 10 to the 17 atoms, right? They want the decay constant. To get the decay constant, all we have to do is take ln 2 over the half-life. So 20.4 minutes, and that's multiplying it by 60, right? What you got? 5 points. We want the activity when T is 0, so we can use A naught is equal to lambda N naught. So you can take your lambda value, 5.66 by 10 to the minus 4, and multiply it by a N naught value, 1.92 by 10 to the 17. How much is that?
Thank you.
1.09 by
10 to the power of
10 to the power of 14. Check well. Now they want the activity after 8 hours. So A is equal to A naught e to the minus lambda T. Right? A naught, we found A naught a little while ago. 1.09 by 10 to the 14. E to the minus lambda. Lambda is 5.66 by 10 to the minus 4. And the time is 8 hours, right? So that's 8 hours by 60 minutes by 60 seconds. Of course, it should be a smaller value than part 3, right?
I see you on virtual Zoom, so I'm sure. And I'll run to people.
And 28 by 10 to the 6. Yeah. All right, let's nice. Pick up one. No. No break.
Yeah, seven.
No.
Seven.
Good. So there's been more time on you. Ah.
2 minutes, man.
All right, done. No, it's your mind. I'll give any break after. Oh, right. So what are the electrostatics? What are the main thing in electrostatics? We are talking about charges. We are talking about capacitance, very important. We talk about Coulomb's law. right? Electric field, strength of the electric fields, and potential difference and so on, right? So we're gonna take a look at that and do a couple of questions on it. Right? We have to focus on electrostatic and electricity. Right? Magnets. Do a little thing on that. That's a 2 minutes sitting down break. So you don't want to leave. 2 minutes, huh? I gotta start in 2 minutes exactly. Now you're moving from it. Alright, online, so we're gonna take a look at electrostatics now, right?
I have 20 when you at the end.
Pick up. If I'm going through, I see this here. People not paying attention here. I don't take my phone. Yeah. Now it's like on normal take what I do it for I actually do it. Yeah.
I forget all this. Like all of this charge and things.
That's just because I spent so long. Potentially viable. Oh, yeah, exactly. This is just like yeah, man. I don't know how I do all this shit.
Alright, let's go. Alright, so we're going with electrostatics, right? Ready? Everything here, so I'll use the hand up, right? Ready? Ready? Right, listen. Alright, so electric field, right? Electric field is defined as any region where an electric charge experiences an electric force. Okay? So around these two electric charges here, right? You have your electric field. Electric fields go towards the negative and away from the positive. Nice. How you work on the direction? Real simple. Place a positive charge around the electric field, and the direction that the positive charge will move is the direction of the electric field. Okay. Always remember, away from the positive towards the negative. That's all, right? Right? How do we measure? How do we determine the strength of an electric field? Well, the force exerted per unit charge. Right? That's the strength of the electric field. Right? Electric field strength is given by N by Newton per coulomb or volts per meter. So it means that there's a next formula. Electric field strength is also what? If you have two parallel plates, if you have two parallel plates separated by a distance d, electric field strength is the potential difference between them divided by this separation. You are going to plate.
Oh my God.
Right? Now I think I'll be doing something mother and I can see what time is up. All right, nice. Right. One thing that we need to remember about electric fields, about the electric field strength is a vector quantity. Okay. So simple thing, if you have a charge in the middle here, and it has, for example, two electric forces acting on it, then the resultant of those two electric forces will be the direction of the electric field acting on it, right? So if one positive and one negative, let's say end up to the right, then the electric field strength will be positive, right? To the left will be negative, right? We will look at a calculation on that. So please remember that electric field strength is a vector quantity, so the direction is very important. That's okay? Right? We should remember that for unlike charges, they attract, right? Unlike charges, they would attract, like charges, they will repel. Right? So for example, here, if you have two parallel plates, please remember when you're drawing the three lines, draw them nice and even, right? Nice and even. Right? So if I give you a charge, right, and you want to find the electric force on that charge, remember from this formula here, F is equal to E by Q. Right? If the charge going between two plates, sorry. If the charge moving between two plates, right? Then the force exerted on that charge, let's assume it's probably negative. The force exerted on that charge is equal to the charge multiplied by the electric field strength, which is given by V on D. So the electric force, as you will see here, is V by Q all over T. Right? So that should be capital V, right? Capital V meaning voltage. Voltage by charge all over T. No, if the charge was negative. I just assume the charge negative. So, that's technical. Okay with that? Right, remember we used this earlier, right? We used this in whose theorem? Well, not theorem, but whose experiment? Millikan, right? We did Millikan experiment, right? When we kept the charge stationary, that was the force exerted on it. Right? Motion of a charged particle in a uniform electric field. Everything that happens here is very similar to projectile motion. So for example, if I said to find the acceleration of a electron moving through a uniform electric field, all we need to do is find the force and divide it by the mass of the electron. Right? I just showed you how to find the force. So just divide it by the mass and you'll get this formula here. That E means that E is a subscript, right? That E is this mass of the electron. Okay? So if I ask you to find the acceleration, all you have to do is take the force and divide it by the mass. All right? Questions like this could come like a projectile motion question. So everything from projectile motion, you could apply it here. Okay? So what that means is that you have to remember your equations of motion. Right? You have to remember all of these, right? V squared is U squared plus 2AS. V is equal to U plus AT, and S is equal to UT plus a half AT squared. All of those are for vertical motion. Horizontal motion is speed is equal to distance on displacement and time. All right. So you need to remember those things because as this little line here says, is analogous to projectile motion. So you have to be able to reach the time projectile motion with this here. Immediately it becomes paired. Yes. Now, y is equal to half AT squared is this. Is the equation. Right? So the same thing from there. But you want me to half u plus v by t? You know where to use that. Right? Next, we have to remember about Coulomb's law. Right? If I give you two charges, Q1 and Q2, separated by a distance r, then the force exerted, right? The force of attraction between them, Coulomb's law, is given by Q1 and Q2 all over 4 pi epsilon r squared. Epsilon is a constant here. It's the permittivity of free space, right? It's the permittivity of free space. Right? Suppose I ask you now to find the electric field strength at a point. We know electric field strength is F on Q, right? Yeah. So if I put this F in here, what will happen? One of the Q's will cancel off. So this formula here, which is Q over 4 pi epsilon r squared, can be used to find the strength of an electric field at a distance r from a charge. So if you have a charge here and you want to find the electric field strength by the x, right? All you have to do is get the distance and the charge. Finding the electric field strength at a distance r away from a charge of magnitude q. All right. So it's a distance r away from a charge of magnitude q. Q over 4 pi epsilon r. If you don't see these here, sometimes it can be tricky. Okay, they come tricky. All right. Next, electric potential. Just like the formula W is V by Q, the V is equal to electric potential, which is W over Q. Right? So we can find the electric potential at any point around a charge. Same concept that we just did, right? Work done is the force by the distance moved. Let's say the distance moved is R all over Q. What will happen, right? We know that F is equal to Q, according to capital Q and lowercase q, right? All over 4 pi epsilon r squared. When you multiply by r and then divide by q, q's will cancel and one of the r's will cancel. So what that means is that electric potential is q over 4 pi epsilon r, right? That's the next way to find electric potential. SI unit is volts, right? Capital P. Right, that's very good. And electric potential is a scalar quantity, right? So the direction doesn't really matter, right? It's a scalar quantity. So a negative value is just a negative magnitude and it will be out like normal. it does not show direction. Yeah, the arrows can cancel. So you have R alone. Huh? Sorry? Well, it doesn't, yeah, but yeah, it doesn't. Yeah, there's like different parts in it and break it up. Right here, I have a little table just comparing gravitational field strength and electric field strength. Gravitational potential, electric potential, and well, Coulomb's law and gravitational force. I didn't write it here, but right, Newton's law of gravitation. So it shows you how we can compare gravitational field and electric fields. Okay, so same questions that you would have gotten in unit 1, module 1, on gravitational fields, they could get the same thing in electric fields, right? Right, and well, I gave you the full breakdown here, right? Right, Newton's law of gravitation, Coulomb's law, gravitational field strength, electric field strength, electric potential, sorry, gravitational potential, electric potential. Which one? G is gravitational field strength. Phi is gravitational potential. Yeah, that came one of those. Yeah, Jim Bow came on. Yeah, not before. No, that's what
No, last year feeling it for process. Last year. No, this is again. I just I do like realize that I don't like that.
Right, capacitance time. Right, the capacitance of a conductor is the charge stored per unit potential, right? So capacitance is Q1V. SI unit, farads. You'd always recognize that capacitance is very small, right? So you would always get a value in microfarads. All right. Right. Remember that we could also find capacitance between two parallel plates separated by a distance d, where the area of the place is A, and it has a material of permittivity E in the middle by using right epsilon A all over C. Right? So there are two ways we can find capacitance, Q1V or epsilon A and B. It just tells you if charge would pass through a substance, how fast or how easily it can pass through. Right? It gives you, so like for example, water has a higher permittivity than like air or something. Right? Anybody could explain our capacitor charge? Yeah. Using that diagram?
Yeah.
Can we open today? Let's see. Right, anybody can explain it? How does the capacitor charge? So when it connects to one, is that charging or discharging?
Discharge.
When the switch connected like that to one, that's charging, right?
Yeah.
Right, and when it goes to the next one is?
Discharge.
Oh, I'm no worry then. Right, so when you connect it, what is maximum? What will be flowing in the circuit? The electron will start to flow, right? So what value will be maximum? Across the capacitor. Current, so think about the three graphs that we had to learn. Current, voltage, and charge. So does the capacitor have any charge? No. Is there any voltage across the capacitor? No. But any current flowing when the switch flows? Yeah, the max current will start to flow through it, right? So if you remember, here's what has happened. What has happened is that when you close the circuit, electrons will begin to flow. The electrons will build up here, right? Right, the electrons will build up. Let's call that plate A. The electrons will build up at plate A, and electrons conversely will leave plate B. Right? So plate A will become negative, plate B will become positive. Now that there's a positive and a negative, they are polarities. So now we will end up with a potential difference. As current continues to flow, the potential difference will increase, and of course, the charge also increasing. That's okay? When does it stop? Right. When the potential difference across the capacitor is equal to the EMF of the battery. That's okay? So your graph will look like this. Current flowing from a max, right? So current will look like this. Right? Voltage starts at 0, so voltage will look like this, and charge will also look like that. That's okay? That's during charging. Right? Lithographs here, lithographs here. The panic. Alright. Okay. Voltage and the formula. The explanation on top there, right? Voltage and the formula. That Vs is the max value, right? Oh wait. It's making a sense.
So I guess that would be take one.
I know, PH in the middle here. All right. I'll draw the graphs here, right? Right, question. Which graph is the first one I drew? No, I didn't draw voltage. Voltage was there. The one under voltage is what? Charge. Because charge starts at 0, right?
Yeah.
So the formula would be Q is equal to Q naught 1 minus E T R C. And the last one is what? Current. So that will be I is equal to I naught E T R C. No 1 minus, right? No 1 minus. Right? Question. When I put it in discharge now, what do you? When I put it in discharge now, what will the graph look like It can't shoot. What do you think the graph of charge will look like?
So start from the high. Yeah.
Right? It will start from maximum and just decrease, right? So that's charge versus time. So Q is equal to Q naught e to the minus T on RC. Right? What would current look like though? The opposite. So when you connect this circuit, no current gonna flow. It will be the same thing, it will be max. Right? It will be maximum and flow like that. Right? Because when it close, you have current flowing, right? So the current will start at a maximum value. Yeah, RC is torque, which is your remember time constant, right? Tau. So where oh yeah. Sorry. All have negative T, right? Right? It's a flip by exponential graph. Why? That's really important. That's why we take my time and going through it. All right, so we need to remember this, right? Are you okay with that? So we have to know the graphs and we have to know the formulas that go with them. Right? There's only one that kind of different. That is the current in the first one. Right? Current in charging. Okay? And you have to be able to explain it, right? Right? RC now, let's take a look at what RC. Hey, tomorrow we're not watching no game. I'm in the mood.
No, I just fully.
I don't want to come and tell me not to watch the game.
No, entra TV na atas.
Huh?
Entra TV na atas.
All right, let's go again. Right? So here we have our formulas. RC is called time constant, and it is the time taken for any value, I or B or Q, to drop to 1 on E of the maximum value. Right? So the time taken for it to go to 1 on E of the maximum value for anyone, B naught or Q naught or I naught, that's what we call time constant. Right? And time constant is RC. Right? The resistance and capacitance inside the circuit. We have to remember capacitance in series. What's the formula?
One of us team.
Right. Capacitance in series like resistance in parallel. And then be able to prove it. Yeah, you have to be able to prove it, right? Capacitance in parallel, you have to be able to prove it as well. Capacitance in parallel is like the resistance in. Right? And last thing we have to remember how to find energy stored in the capacitor. Any one of those could work. Right? Any one of these here could work. All right. Let's try questions, huh? Pardon me, sir. Sorry. Yeah, you can work on the other. So just make sure you know one. Like the first one, right? I have QB. And it gives you the integration. So if they get 11. If you get 11. All right, let's go past people. Right, 24 was magnets. Twenty-three is grass, like we will still try it still, but I don't for sure, I don't want no grass, I don't want no grass. Alright, we'll come back and do 23, let me start with 23. Yeah, I'll do up the party, not the course. Oh, I don't want to. I don't want to.
Yeah. I get it. I second class for 60. Raj, you get 60.
Alright, let's go. This is 1942. Alright, let's go. Alright, you want to do everything? Or the calculation?
That's the calculation.
Describe the procedure involved in storing a quantity of electric charge on an initially uncharged parallel plate capacitor. Huh? No, this is what we just did. Anybody recognize this question? They did the diagram with the capacitor with the switch at one.
Oh yeah.
Right? So you have to explain charging. Okay, so see if we can join back and explain it now. Draw the circuit and explain it back.
This try for the good boy. So you like how I sound?
Right, so the first thing you'll do is draw back the circuit, right? You have to draw it, it'll be easy way to explain. God, we need a graph for this one.
How do you ask?
All right, so well, yeah, part 1 and 2 is basically what we talked about a little while ago, right? Draw a diagram, first step, tell them draw a diagram, set up as shown above, right? Second thing is tell them to connect the switch to label it up, right? Connect the switch to 1 in that case, right? And as soon as you connect the switch, right, the electrons will leave the battery and begin to build up against one of the plates. You have to label the plates, right? You have to label the plates, right? And the electrons will build up there. And as the electron build up on one side of the plate, the opposite side of the plate, the electrons will leave. That's okay? There's about 4 lines there, right?
Yeah, just
Yes, you can make a.
Step, draw a diagram fast. It must have a diagram, otherwise you have 10 things to explain. Draw the diagram with a two-way switch.
It's not like a 4 lines. We're doing that. I'm inside right.
Once it's in the space, there was everything at one time. The diagram is to help you make your explanation simple. Yeah, anywhere outside, see this line here? See this line up here? Anything inside that, you can see. Well, not me again, but people can see. Right? Anything outside here, we can't see. Right? So you could draw right here. So like this little space here, draw your little diagram. Right here, draw your little diagrams. Right, step 1 right here. Take your pen, hold it in your right hand or your left hand, put your fingers around it, and write number 1. Right? That's okay? And number 1, you're right. Set up as shown in the circuit. Circuit will help you here. No, if you draw a circuit and do explain to get 0. Right? You draw a circuit to help you explain it. Step number 1, connect as shown above or to the left or wherever. Step number 2, turn the switch to 1, right? So if you use this setup, label it 1 and 2, and label the plates X and Y, right? And plate battery, right? Right, turn the switch to 1. And when closed, electrons will leave the negative terminal and build up at the. It will leave the negative terminal and build up at the plate Y.
Number 3, right?
That's number 2.
Let's close the switch.
Okay. Number 3, the electrons will build up at plate Y. And 3, electrons will leave X and go back to the positive, go back to the supply. It will leave X and go back to the supply. This will store quantity of charge on the plates, within the plates. This will store quantity of charge within the plates. Explain the movement of charges. What will happen? The electrons are moving from the negative plate to plate Y, and then from the plate X to the positive terminal of the supply. Oh, by the way, say this anyway. If you draw a diagram, you don't have to say this is supply. because the battery is DC.
What was the step after they say quality of charge between the plate, this will take something. What was the step after?
It will be accent to maximum this was 12 of charge of the medium.
Yeah.
All right. So you have a diagram here. I mean a resistor, a micrometer, and a capacitor. They gave you some readings for discharge, and they wanted to plot a smooth curve here. What would the curve be shaped like? Right? Remember we just did it, right? This is charging or discharging. So it will be shaped like that, right? That's okay?
Yeah. Thanks for that.
Nice smooth curve, right? Right? Next part. Everybody okay with that? So the time constant for the type of discharge curve obtained in P may be defined as the time taken for the current to decay to 1 on E of the original value. Right? So just trying to explain here for the non-math people. Use this definition and the graph to find the time constant. So all you have to do is to find what? What you'll do, kill it to find the time constant. Remember what it is, right? The time taken to go to what? 1 on E. Let's tell you there. 1 on E of the initial value. What was the initial value? 17. So go to a graph and find 1 on E of 17. Wait, no, sorry. Go to a calculator first and find 17 on E. E to the power 1, right? 17 divided by E. 6.25. For somebody who plot the graph, just tell me what 6.25 corresponds to now.
Yes, no.
6.25 go across and come down and tell me what time it is.
Yeah. 6.1. Yeah. Close to 6.
All right, so let's say about 6 seconds, right? Yeah. So the time constant tau is about 6 seconds. You okay with that? So just to read it off, right? So after you plot your graph, let's read it off. By this time tau again, what's the formula of tau again, Sean? T is equal to what? No, tau is just RC. Right? Tau is just RC, right? Can you all work on this here? Using this value? Calculate the value of the unknown capacitor. Find C for me now. What was R again? Look back at the table. Look back at the
17. R is the highest value.
no. R was 1. Use this stuff. 1 by 10 to the 6. R is the resistor in this circuit there. See that? R is this. And C is what we're trying to find. So R is 1 by 10 to the 6.
It covers 6 seconds. Okay.
So it's 6 seconds divided by R, which is 1 by 10 to the 6. Sorry? Oh, I am now on part 2. Part 1 was 6 seconds. Part 2 is 6 microfarads. You okay with that, right? You okay with that? Try this, please. Calculate the charge on the capacitor before the switch is closed. What is the charge on the capacitor before the switch is closed? What's the formula we use in the tree? Right, we found the capacitance to be what's again 6 microfarads. Sorry, Q is equal to CV. So we know what C is 6 by 10 to the minus 6, and what was the original B value? Huh? Can you give us that somewhere?
B is equal to IR to give us resistance and I derivative resistance and current. B is equal to IR.
Oh, I thought they gave us the supply, no?
They give us resistance and they give us the current. Yes.
Right, sorry. Right, so here they want us to find the voltage. Voltage is current by resistance. The original current was 17. Huh? Right, and the resistance was 1 mega, right? So multiply it out. 1.02 by 10 to the minus 4. Do the last part, please. Sorry, second to last part. Right? What's the formula we'll use here, Ariane? The capacitor consists of 2 metal plates separated. The capacitor consists of 2 metal plates separated by a layer of insulated material 0.5 millimeter thick. And they give you a dielectric constant. Sorry? Epsilon A on D. Okay. Right, start with T, please. Sorry, start with A, please. We know the capacitance, we know epsilon, and we know A. And D. What? Epsilon. Yeah, dielectric constant. So it's dielectric by epsilon by E. So let's rearrange it, and you'll get A is equal to CD all over 450 by epsilon. Yeah, it's on the page, yeah. Right, C was 6 by 10 to the minus 6. The value for D is 0.5 by 10 to the minus 3 by 450 by epsilon is what? 8.85 by 10 to the minus 12, right?
0.75.
Book it out, tell me what you get for E.
0.75.
0.75 meters. Yeah, the whole question to pass it up. Last part, Asaria, what are we doing here? Try that last part, please. Right, so show by equating work per unit charge and moving it positive charge Q from B to A, that E, the strength of the field between A and B equal to the potential gradient. So they told you what he equate, right? How am I writing that, Zaria? How am I writing that? They said by equating work per unit charge is equal to voltage gradient. Right, so they wanted to show that the electric field strength is equal to the potential gradient. So we can use the formulas now. Oh no, they're not here. Well, they need summaries. So we can show that now. The last one. Huh? Yeah, and it will get out. You want to show how electric field strength can make E up. E is equal to voltage. It will be beyond. Yes, well, R. No, but it's not. This is what we talk about. My job is on C. Start quick.
You pretty good. That's what right. You pretty good. But that's when I reach. I see you. I didn't make them last year. Really exact same as anyone. So you know. I feel like that. Yeah, sometimes I know what exercises. Was I knew? Yes, I didn't know it.
Right? Now looking okay there? So you have work done is equal to force by distance, F is equal to EQ. Remember the objective is to find electric field strength, right? Huh?
Leave it that.
Right? So that's correct there, right? What was important is that you identify what you're starting with, right? So you start with the same formula for work done, and then you substitute F. The objective is to make E the subject of the formula. And in making E, you'll be able to show that E is equal to the change in potential gradient, right? So the electric field strength is equal to the potential gradient. All right. So then next day we'll continue. We'll do some questions on electric field strength and potential, some more like this, and then we do electricity. Watch it good.